Alright, let's talk about domain of functions. So we kind of talked about the limitations with radicals, specifically with square roots. The inside of that square root needs to be more than or equal to 0. So if we're taking the square root of some expression, whatever expression is inside there has to be more than or equal to 0. So that's going to be something we use for radical functions. For rational functions, where we have some numerator expression divided by some denominator expression, the rule we need to use is that the denominator cannot equal 0. So something we use for the domain there is that whatever's in the denominator cannot be equal to 0. And then we'll take a look at some quadratic and linear functions and how those don't really have any limitations to the domain. So part of this will be recognizing what type of function we have. So this right here is linear. That's just going to graph a line. And the idea is going to be that for domain, we can plug in absolutely anything and we'll have an output. There's nothing that we plug in that's going to break the function. So with this is a case where we would have all real numbers, which a symbol you might see with that is our symbol for real numbers. So you might just see this kind of fancy R. We could write an interval notation, which I'll do for all of these. And for all real numbers, we would just say from negative infinity up to positive infinity. Let's take a look at the graph of that function to see domain. So that function's a line, and you can see there's no breaks in it, there's nothing funny going on, it's just going to be defined absolutely everywhere. Alright, our next function. So you can see the division there, and we have an expression in the numerator, expression in the denominator, so this is going to be rational. So I need to focus on the fact that that denominator, in this case that x plus 1, cannot equal 0. And what I can do is I can solve this just like a regular equation. I'm just going to keep that does not equal, so I'm going to subtract 1 from both sides, and that tells me that x cannot be negative 1. So what that tells me is that we can have absolutely any real number for x, but at the same time, x cannot be negative 1. So if we take a look at the graph of this, what you'll see is we have information absolutely everywhere, but then at negative 1 here, there's nothing. It's creating this vertical asymptote where the graph isn't crossing. So with these rational functions, we're seeing these vertical asymptotes where our function's not defined. So in terms of our domain, we can have anything from negative infinity up to negative 1, and then from negative 1 off to positive infinity. So if I wanted to write this in interval notation, I would go negative infinity up to negative 1, and I would want to use parentheses because I don't want a square bracket since that would include negative 1, but we can't plug in negative 1. And, which I use the union symbol, and then we would go from negative 1 up to positive infinity. So this notation for the interval goes to this idea of skipping over just a single value where we don't want to include that negative 1, but we want to include absolutely everything else. Alright, our next function here, this is also rational. So with this, I want to take that denominator, so x squared plus x minus 2, and say that cannot be 0. And then I'm just going to solve this like a quadratic equation. So I'm going to factor, which would be an x plus 2, x minus 1. And that cannot equal 0. And I'm going to separate it up. So x plus 2 cannot be equal to 0. X minus 1 cannot be equal to 0. So x is not allowed to be a negative 2. X is not allowed to be positive 1. So with this, we can have all real numbers, we can plug in absolutely anything, and x cannot equal 1 or -2. So with this, in terms of interval notation, I'm going to write kind of similar to what I did up here, in that we're going to start from -infinity, we can have anything out there, up to, but I want to skip -2, so we can go all the way up to -2, but not including, and then we can start just to the right of -2 and go all the way to +1. Then I want to skip +1 and then go off to +infinity. So it's creating these sections where my function can be defined kind of in this negative region between those two values and off to +infinity. So in the graph we can see this coming through with these kind of three sections. We have this vertical asymptote at -2, we have this vertical asymptote at +1 where our graph is not defined. Alright, radical function. So with this, I want to take everything that's underneath the radical, so that 3x minus 12, and I want to set that to be more than or equal to 0. So I'm going to add 12 to both sides, divide by 3, so x has to be more than or equal to 4. So that means for an interval, we can start at 4 and then go off to +infinity. So if we take a look at the graph here, you can see our radical function starts right there at 4 and then goes off to +infinity. But anything below 4, we don't have anything defined for that function. Alright, here's a quadratic. And in terms of domain, we can plug in absolutely anything. Kind of like with the linear function, there isn't going to be anything that breaks this function. And if we look at the graph of it, we have our parabola. We are limited in terms of range, but for this section we're just focusing on domain. And we can just plug in anything and we'll have a corresponding output for the input. So with that, this is just all real numbers. So we could have anything from -infinity off to +infinity. Alright, here's a rational function. And what we're going to do is take that denominator, so x squared minus 5, and we're going to say that cannot be 0. So we'll add 5 to both sides. And then, because I have the square there, we're going to take the square root of both sides. So we're going to say x cannot be equal to, and when we take the square root of both sides, we get plus or minus. And then we'll have square root of 5. So with this, there's two values. X cannot be -√5, x cannot be +√5. So we could say x is all real numbers, and x cannot equal, and you could use the plus or minus symbol for the square root of 5. If we do interval notation, there's going to be two values that we want to skip in the interval. So we start at -infinity, go up to -√5, and skip it, and then go up to +√5, and skip that, and then go off to infinity. So with that, let's take a look at the graph. And we can see, and it's hard because square root of 5 isn't a whole number, but the negative one's right there, positive one's right there for those vertical asymptotes. Okay. Now let's look at 2 where we have a mixture. So this is rational, but it's also radical. So I need to think about kind of two things at once. Overall, this denominator cannot equal 0. So we do not want 0 as an output there. At the same time, inside, I need something that's positive, 0 or larger. But if I think about these two things at the same time, I can actually combine them together because I want, let's see, for radical, I want it to be more than or equal to 0, and for rational, I want it to not equal 0. So what I can do is just adjust my symbol there. What I want to do is make it so that it's just more than 0. So you can solve these separately or together. Like, let's do it separately for this case, and then we can talk about kind of putting it together in the next. But what I would do is say, okay, the square root of x minus 9 cannot be 0. So I square both sides of the equation, add 9. So x is not going to be allowed to equal 9. Then if I do the step that we talked about for radical functions, so x minus 9 has to be more than or equal to 0. So what I would get from that is x has to be more than or equal to 9. But to combine these two pieces together, that x has to be more than or equal to 9, but also x cannot equal 9, what we would end up with is just x has to be more than 9. All I would do is take away the equality piece of that inequality and make it strictly more than 9, so that I get rid of this case where x can't equal 9. So with that, we're going to start at 9 and go off to positive infinity and not include 9 to combine those two pieces together. So there's a way of doing this all in one big step of just solving with it being more than 9 instead of these two separate cases. However, this works great too. So whichever you like better. In the graph, it's a little hard to see, but we're going to end up with a vertical asymptote at 9. So our graph will get like infinitely close to it, but it's never actually going to cross that positive 9. But then we're defined for everything above that value. Alright, let's look at another case where we combine, in that from this denominator, we'll use what we know about rational functions, which is that that cannot equal 0. And then in the numerator, we want to be careful and make sure that what's underneath that radical is more than or equal to 0. So let's take care of the denominator piece first, just figure out what we can't equal. So 3x minus 21 cannot be 0. So 3x cannot be 21, divide by 3, so x cannot be equal to 7. At the same time, x minus 4 needs to be more than or equal to 0. So this is a little different from the last case, because now it's occurring in two different spots. In this last one, it was all together, so it combined a little more nicely, but this one we should definitely do separately. So x has to be more than or equal to 4. So with this, I can plug in anything larger than or equal to 4 for x, but also at the same time, x cannot be 7. So let's kind of put that together, that x is more than or equal to 4, and x is not allowed to equal 7. So what that's going to look like for my domain is we'll start at 4 and go off to infinity, but I need to skip over 7. So we can have anything from 4 up to 7, but not including 7, and then from 7, but not including 7, all the way out to positive infinity. So let's take a look at this graph and see how that's coming through. You can see our function starts at 4, and then it's defined all the way up until this vertical asymptote at 7, where our function's not defined. But then as soon as we get to the right of 7, our function's defined again, and off to positive infinity. So that's how we can algebraically find our domain of the functions. We just have to know what type of function we have, or sometimes it's a combination. But then use the graphs as well to kind of support your answers and double check that you got it right.